Well, now our next sub-article is analysis of voids or holes in a close-packed lattice. FCC unit cell is an example of close-packed unit cell. Imagine that a type of particles have formed a FCC type of unit cell or lattice in general. We know that in such a unit cell, only those particles, 3 in number, lying on a face diagonal are in contact. But the particles lying on an edge are not in contact. That's why its packing efficiency is 74%. It means still there is 26% space empty. We can think of occupying it at least partly by inserting the other but smaller particles of appropriate size. Then a question arises: what are those locations where such smaller size particles can be inserted? Such locations are called voids or holes. In a FCC unit cell, there are 2 types of such voids. They are: number 1, octahedral voids; number 2, tetrahedral voids. For a close-packed unit cell which consists of n particles, the number of octahedral voids are n, but tetrahedral voids are equal to 2n. Remember, simple cubic and body-centered cubic are not close-packed unit cells, hence above formula is not applicable to them. Since n is equal to 4 for a FCC unit cell, hence it must have octahedral voids or O holes equal to 4 and tetrahedral voids or T holes equal to 8. An octahedral void means that if a particle is placed into that, then it must be surrounded immediately by 6 other particles. That is, its coordination number must become 6. We have already seen that in case of ions, for coordination number 6, that is octahedral geometry, r plus upon r minus is equal to 0.414, or it must be somewhere within the range 0.414 to 0.732. Although we had derived the above relation as radius ratio for ions, but it can be generalized as radius of the guest atom upon radius of the host atom is equal to 0.414, or within limit from 0.414 to 0.732. Mark it as condition A. Then the coordination number of guest atom will naturally become 6, and we can say that it is occupying an octahedral hole in FCC lattice formed by host atoms. Similarly, for tetrahedral void or T hole, we can write radius of guest atom over radius of host atom is equal to 0.225, or in the range from 0.225 to 0.414. Mark it as condition B. Therefore, for inserting a gas atom or ion in an octahedral hole, the condition A must be satisfied, and for T hole, condition B must be satisfied. Now we can proceed for finding out the locations of holes in a FCC unit cell. As shown in the following figure, suppose that a FCC unit cell is made up of particles represented by dark dots. These particles are occupying all the corners and all the face centers of this unit cell.